Good evening, everyone. Well, good evening, good afternoon. I don't know where we are here. On the West Coast, it's afternoon, and I guess on the East Coast, it's evening. My name is Nüsret Hisim, and my colleague Melissa Hill is here. Let me get the show on the road. So we're going to play around a little bit with Voltaic cells today, but just a little bit about us. Melissa, why don't you tell everyone a little bit about yourself?
Yeah. Hi, everyone. I'm Melissa. I'm one of the chemistry staff scientists at Vernier. I've been there almost 13 years now, and I do a lot of this kind of technical support and training stuff. I also help with product development, curriculum development, and software advising, I guess you could say. And yeah, I will be answering questions in the chat, and I will also be interrupting Noose with questions and anything that I think would help the experience. So definitely, again, put all your questions in the chat, and I will make sure Noose gets them, or I will answer them in the chat.
Sounds good. Thanks, Melissa. My name is Nüsret Hisim. I taught chemistry and physics in Maryland for 34 years. I've known David Vernier since 1984. He started the company in 1981, way back before internet and all that fun stuff. There was a thing on Twitter today about graphical analysis. He wrote that thing back in the 80s, and I used it with my students. But a few years ago, they needed help here in the chemistry group, and so in 2016 I came to the office, and it's been a lot of fun. This is a great place to work. If you ever have a chance to come out here, we would love for you to come and visit us. So let me tell you a little bit about the motivation here. I taught for 34 years. I taught AP Chem for 25 years, every level from, of science, particularly physical science, from ninth through AP. In 2011, I read exams, and I guess I was a little bit surprised with how few students attempted the electrochem questions. And I just went back and pulled, the last 10 years worth of exams, and 5 of them have these are screenshots of 5 of them. And I think 4 of them are voltaic cells. And it's just really a shame when students don't try this question. Even if you can only spend a day or two on this topic, I think your students, particularly AP, but I mean, every student loves to make a battery and loves to see if they can get the highest voltage, and it's just so simple to do. And if you do, even if you just do it with a lemon, I think you should do it. It's just really eye-opening, and you can look around and find different types of metals that you can use and so forth. We have a couple experiments in our lab manuals that do this. And the voltaic, I like this voltaic cells one just because it's so modeled after what one looks like, in literature and in textbooks and things like that. By the way, I put this up here to remind myself, I've got files for you. I've got data files and instructions for this experiment in a shared folder, and you'll get a link to that. If you need it sooner, send me an email and we'll talk about that later on, and I can zap it right out to you. Super easy equipment. I like these well plates. I think they're cheap. They're beautiful. They make a nice little micro cell that I think looks real nice, and you'll see it in a minute. So let me get the camera up here. Let me make sure I didn't miss anything. Yeah, we'll talk about that stuff later. So I got a camera set up here so you guys can see what I'm doing. Let's get graphical analysis up on the screen. So I'm going to use our GoDirect voltage probe just because it's so simple to use. It's wireless, cuts down on a lot of annoying things, that you might have with other systems. It's very, very clean and easy to use. And so I've got my microcells here, and I've got some electrodes. We need to soak some salt bridges. So let's get that going here. So I've got some potassium nitrate. Let's get a little into a well, and we'll soak. So these are just 2 centimeter cotton strips. This out of the way because we shouldn't need that again. I did this one. I was surprised. I did this one at BCC last year at Purdue. And I was thinking, oh, these college people, why would they need this? I was amazed the number of folks that just enjoyed this activity. It was just kind of fun to see that, something that I thought was super simple. And it is, it really, as you're going to see here in a minute. But boy, I was just thinking, this is way too simple. And the reception was way beyond what I was expecting. So that was really kind of neat. Just little strips of cotton string. Okay, 2 centimeters. They have to reach from one cell to the other. So I'll get those soaking over there. And so now let's go ahead and get the system set up to collect data, and we'll build our first cell. So on our GoDirect sensors, you push a power button and a little LED starts to flash, indicating that it's ready to connect. I'll click on sensor data collection. This runs in the free version of our graphical analysis software. So I had that question come up this week, and do I have to have the Pro? We'd love to sell it to you, but honestly, you don't. It will work with the free version just fine. You can plug in sensors; it'll work with those. This one's just a slick one because you don't have a lot of wires to deal with.
You connected to the wrong sensor there.
Oh, I just noticed. I'm looking, going, wow, that's really cool, but that's not what I connected to. Thanks, Melissa. See, I get talking and I forget. So what happens is that when you're, let me get rid of this one. So let me disconnect from him. And what I want to connect to is a voltage probe, volt. Don't think there's too many in the room here. There we go. Thanks for catching that, Melissa. So, all right, let's go. That looks better. I want to keep a record. I don't want to just use this as a voltmeter. I want to keep a record. So in the instructions you'll find in the shared folder, I'm going to change from time-based data collection to what we call event-based data collection. But let me make the screen just a hair bit bigger so that you guys can see it a little bit easier. So bottom left corner, you can change the mode of data collection. I'm going to change it to event-based. And I'm going to use the selected events because it's just simple. You'll see it in a second. And the event is going to be the cell that I set up. This averaging, if you have a situation where your data is fluctuating, sometimes that's useful. But for this one, I don't think we're going to need it. Let me turn the meter on too. Let's make sure to start with, at least, that we have a potential of 0 between the 2 electrodes when they're touching each other. So I'm going to take the 2 electrodes and hook them together. And if you tap on the little meter down here, there's an option that says 0. So if the meter, if there was potential when they were connected like that, we don't want that. So I want to make sure that that's 0. All right, let's build our first cell. And by the way, in this experiment, what the students do is in the pre-lab, they do all the half reactions and they have to add them up and find the cell potential. I put a solution to that in the shared folder. So if anybody wants to use that with their students, I would encourage you. That is, the most common question is, given these half reactions, add them up. What is the overall cell potential? And something that's, it does cause a little bit of quandary with kids, because of the, which one do you use? They're all redoxes, which one, they're all reductions. And so, how do you switch one around to the inoxidation? So here's the deal. Let me hold up my electrode. So I've got copper electrode. I've got a zinc electrode. Well, I better not say that. I've got a magnesium electrode. I've got X and Y. So in this experiment, right, and the other thing that when Don wrote this experiment, Don Volz wrote this thing like 30 years ago or more, he used a lead electrode and lead nitrate. And I know some schools have issues with that. So when I wrote this, I rewrote it for BCC last year, I tried to avoid lead. If that's not an issue for you, by all means, use lead. And the original experiment does use lead, but I know there's some issues in some parts of the country where people are trying to avoid some of these, heavy metals and stuff. So I changed it to copper. And then the deal was that, how do I do X and Y so it's not immediately obvious? If I make magnesium, X, I mean, that's going to be pretty obvious. So my thought was the first cell they make is the one is with the magnesium. So let me find my magnesium nitrate. Should be around here. It is. In the original experiment. Yes.
Before you keep going, what were you just doing there with the copper strip? You were cleaning it.
Oh, I was cleaning it off. I'm sorry. I should do that with the magnesium too. You know how these things will get, but particularly magnesium gets pretty oxidized, you know, one of those little more reactive metals. You are going to get better potentials if you clean them up a little bit. I got to be careful with my magnesium. Let's not get him too hot. But yeah, he's getting nice and shiny here. So these are little ceramic discs if you don't want your kids to, you know, tear up your countertops in your lab. Something like that might be useful. If anyone, you know, anyone that's just redone their kitchen or their bathroom, you know, and has some leftover tiles, perfect for this, right? So now it's nice and shiny. Let's get some magnesium nitrate into the one of the adjacent cells. And I love these little barrel pipettes too. I reuse them. I clean them and reuse them. But they are super cheap and they stand up if you want. You know, they stand up very nicely in the. I've used in one of our cuvette holders just to have it out of the way. All right, so let's get the magnesium in there. Okay, now watch me carefully. Did I screw up? So I'm going to connect my electrodes. This is, I think it was 2018 in the AP exam. This was the question. What's wrong with this Voltaic cell? And what the students, you know, I've got it all hooked up. Shouldn't I be reading a voltage? They forgot to put salt bridge in. And so what a cool thing to do is let the students maybe discover that. You know, what happens if you leave out the salt bridge, you know? So let me put that in there.
Noose, we just got a question about why you're using nitrate instead of sulfate.
Because it's very soluble and it was handy.
But, yeah, it doesn't matter, right? You can use whatever you have.
Doesn't matter. In fact, in the lab, I didn't have aluminum nitrate. I had aluminum chloride. So that's what one of these is. It's all we care about is the metal ion. So okay, voltage is highest. Let me grab that. Okay, and what we should do, and we have 30 minutes here, so I'm not going to. If I do want to do all of these, I can't do this, belabor it, but you should take it apart, clean everything, put it all back together and measure it again. But I'm just going to go ahead and do 3 runs just to kind of emulate the experiment. But you know, ideally you should try to get your highest voltage and you know, clean everything really well in between. But I'm not going to do so. There we go. There's my 3, and then I'm going to. So with event-based data collection, you don't stop until you've finished, you know, that part of the experiment. And you can see that each time I collect data, it grabs a point. It doesn't care how long you wait. There's like no hurry involved. Okay. And so, you know, I probably should have waited a little longer because look at those potentials. They're eking their way up. Why don't I grab another one just to have it? Okay. And so, yeah, but there's no rush. And if you mess up and you stop and you go, oh no, I need to do another cell. I hit collect and I say, I need to append to my data set. Now I can do another cell or, you know, clean it up and do another one if I want to. So that's something to be aware of with event-based data collection. And so now what we're going to do is we're going to make another one. So but it's always going to be against copper. So let me take this apart. Another beauty of these little well plates is I can make one right next to it here. I'll get this out of the way just so it doesn't make a mess. Let's see. Oh, so in the pre-lab, the students have to do the half potentials for zinc and aluminum. And so check out the pre-lab. It's in that when you go to that shared folder. I should show it to you just so that you know I'm not lying to you. There's the shared folder that you guys will have access to, and the pre-lab. Here's the solutions. I worked them out just so it's always nice, especially if you're new to eChem. It's nice to have a little bit of guidance on how to do stuff. So here is the copper magnesium, copper zinc, and copper aluminum cells, and worked out, all these numbers, of course, came from the standard reduction potentials. You're not going to get those numbers with these kinds of little easy peasy cells, but you'll get the trend. And that's kind of the most important thing with this experiment, measuring the potentials and learning how to write these equations. That's, I think, probably the most important thing. Some people ask, can you do this with the free version of graphical analysis? You can. The pro version does allow you to have some nice pretty bars on your graph if you want, which the free version doesn't. And here's one experiment where that might actually be something fun. All right, so let me take electrode X. Let me clean him up just a hair bit here. We were practicing yesterday, so these got a little oxidation on them. And yeah, sulfate, fine, chloride, fine. I mean, it would be nice to be consistent, but in most cases, those salts of these metals are going to be pretty soluble. So the other issue, is do you have any disposal issues? That might be something. X, here it is. You probably wouldn't put a label on the bottles quite like mine, but this is for my training and for myself, right? And so let's put it adjacent to the other side over here. And so fill that cell up pretty much all the way. Get that out of the way so I don't mess it up. Put the electrode in. Oh, we learned something from the last time. Let's get the salt bridge in there. I found these tweezers on Amazon for like 50 cents a piece. What a great, if they get messed up, who cares, right? All right, let's see. We got that cell connected. This time when I collect data, I am going to create a new data set. Okay, because now I'm going to have this set of copper X voltages. So we'll keep that one. We'll clean everything up, time lapse, and then we'll put it all back together and we'll do the next one. In the experiment, it says to do it 3 times and then do an average value. So just pretend that I did that. All right, here we go. Done. And so we've done that one. And then what we do is let's do the third one. And so we'll put let's get that bridge out of there just so it doesn't interfere. Oops. Oh, wait a minute. The third one is Y. Let me clean him up a little bit. Yeah, the other thought was when I was going to Purdue last summer, I was like, I don't have people using steel wool on Purdue's lab stations. They'll never invite me back, so that's why I got these little discs. But like I said, if you can get scraps of tile, wall tile or floor tile, I used a lot of stuff like that. Sometimes you go to the hardware stores. I did this many times. Go to the store and say, hey, I'm a chemistry teacher. And do you have any leftover keys or do you have any leftover, stuff? And they're so nice. Some people are so nice, So anyway, this is Y. Right. So there's unknown Y. Let's get a bridge in there. And let's hook him up. All right. And so let's grab. So, oh, wait a minute. I didn't stop the last one, did I? I need to stop. Okay, because that was the last one. And actually, what I should be doing, and I apologize, I'm kind of going quick here. The first one I'm going to rename. I'm going to call that one the copper zinc one. Was it copper zinc? No, it was copper magnesium. And then the second one, what I just did was the copper X one, because they wouldn't know. The idea would be to go back and look, look at the potentials, compare that to the pre-lab, they should see a pattern. They probably won't see the exact value, but they'll see a pattern. Okay, now let's do another one. Create a new set and let's grab them. So grab, take it all apart, clean it all up, put it back together. Grab, take it all apart, clean it all up, put it back together. Grab. Okay, so we're done. And so that one is the CU-Y set. And then let's put them all together so we can compare them. So I tap, I don't really need this voltage or the table anymore, but let me get rid of those just to make it bigger so you guys can see it better. And so I can turn on the other two that are still there. The way graphical analysis works is it automatically saves your runs in the background. And, you can play all kinds of games with colors. If this was magnesium, so I don't know what color magnesium is, a darker color maybe. And so, you can play all kinds of games like that. Let's make this one green, just because. So any thoughts, questions? How long does it take for the salt bridge to be ready?
Yeah.
Oh, well, you saw it. About a minute. They can sit in there forever. I mean, I don't know about forever, but it probably is ready in 10 minutes. And I would just, if you don't want your students to do what I just did, you could just have a couple of beakers or something. It's it's a 1 molar potassium nitrate solution, and I tended to use a lot of those communion cups. I would wash them out at church, and I would take them to school, and I would use them for stuff like this. So you could put a whole bunch of them in a cup and have them ready for your students if you didn't want them to have to cut them, or but it's just normal cotton string. Any other thoughts? Yes, and dip it in the cup. Yeah,
there's just been a lot of talk of different options to use for the salt bridge. And so I can imagine definitely what you decide to use as your salt bridge. It'll vary how long you want to dip it in there, because filter paper would be ready real quick and you wouldn't want it to fall apart.
Jack told me to use filter paper, and it was like, yeah, okay, but that's, I mean, coffee filters would probably work. I wanted to show you that question. It's this one right here, the top right, 2018. Look what's wrong with this, and so let the students experience that. Leave the bridge out. Why do you need the bridge? It's kind of neat, for them to do that. So, but think about it. We've been going, let me look at the clock, 23 minutes, not counting, and that's with all the intros and stuff. Could you get this experiment done in a 47-minute class period? Absolutely. Okay. It might take a little practice on your own to kind of to see, what to do. But you could do this thing in a normal class period pretty easily. And I think it would be super cool to use 1 molar solutions, like I see some people are suggesting, and see if there's a difference. I mean, the standard cells are 1 molar solutions. And so, the ones for the reduction potentials chart. So try it and see, how much difference it makes.
His question is more about, do you have the students calculate for the non-standard condition? Or, I mean, if you're just using this to look at the trend, then you don't necessarily have to have them recalculate, but you could, right?
You could. There's actually, and this one, once again, it's a lead copper concentration cell. There is that extension in this experiment, and it is in the download. So when you download it, you can take a look at that. There's also a copper ammonium complex that's also an extension to this experiment that some people like to do. But the basic Voltaic cells, I really hope more people do it. You've got, especially if you do teach AP particularly, but that doesn't have to be, but exam's going to be the first week of May. So, squeeze in a day or two. The other thing, and I'm just going to, Melissa made me take this down. So I kind of took it down and I kind of didn't. is electroplating. Oh my gosh, the students love this. I use to do this. Vernier has a very special sensor, the constant current sensor, and I used it with the LabQuest yesterday. I put all the data, all the stuff you see, the numbers, they're in the shared folder if you guys want just the numbers, but there's the original key, and then up there hanging from the sensor, there's the the copper coated brass key. Kids love to electroplate stuff. It's like, it's a really fun thing to do. And also a little more mathy, right? So you got to kind of get in there and talk about current and charge per second and stuff like that. But it's, very good. There's another experiment in the advanced book that has the students calculate a value for Avogadro's number. Remarkably good data comes out of that. And it's an EChem experiment. We have 4 sensors that are directly related to teaching electrochemistry. You saw the voltage probe in action, and you saw my constant current sensor hanging on the side there. I used it yesterday. Those are extremely useful for this kind of study, for students. If you want to see how an oxidation reduction can change over time, then you can do a titration, an oxidation reduction titration, and our redox sensor, our ORP sensor, is very, very good for that. And then at a higher level, if you want to change current and voltage and see how that can drive a reaction, then our cyclic voltammetry system is really, really neat to do that. Look, that's a higher level than high school for sure. I never taught anything like that, but it is very, very cool to watch how that thing progresses. I saw some stuff pop up there. Is there anything I need to know? Anything I can questions?
People are just kind of sharing their thoughts and ideas. We had a question about the Avogadro's number. If it was in the Google folder, and it's not.
Oh, I'll put it.
Oh, okay. Noose will add the PDF of it. But it's also in the advanced chemistry book with Vernier. So if you have access to that book, if your school has purchased the site license, definitely get the download from your Vernier account. And then it'll be the latest version, because we keep updating these periodically. So always make sure you have a Vernier account so it sees what books your school owns, and then you can get the latest version.
Yeah, well, I thought I'd put that in there. It's experiment 21, and I'll make sure it gets in there. What I like about that one is that, Avogadro's number, where does this come from? Did somebody try to count that?
It already is in there. Sorry, it is in there.
Oh, it is in there? Yeah. It's
I was looking for a different title. I thought it was a different title.
Oh, yeah.
My bad.
Yeah, it's just
electroplating.
Yeah. But anyway, that one, the whole idea of coming up with a fundamental constant of nature. I mean, it's like, I almost get as excited for that one as physics teachers do for getting the value for G, right? Because it's like, it's a fundamental constant of nature. G is not. It's the Earth, but there are other planets, and it's just kind of cool. And it does use the same type of math and thought process as the electroplating lab for doing the key. So I'll make sure that both of those experiments are in there. If you want to try it, it uses the same process. It's just a little different the way it approaches it in terms of the math, so that you can come up with a Faraday's number and all that kind of stuff. Anything in the last couple seconds here? Anything that we need to talk about?
There was a question about the GoDirect cyclic voltammetry system, and that is one of our newer electrochem instruments. And it's a little bit too much to describe right now in the last minute. So I'm just directing people to the main webpage. There's a little video that kind of goes through and tells you the different types of experiments that you can do with it. We also include 5 free experiments with that instrument, and those are available free on the website, so you could just look at those experiments and see what you can do with them. But one of the best ones is just like identifying the concentration of Tylenol in children's Tylenol. So
That
you can do
is one
lots
I can
of
understand.
yeah, you can do lots of things with it.
Yeah.
But we'll have to do maybe a webinar about it another time.
Yep. Sounds good. All right, folks. I appreciate your time. I'm glad that that sounds like a few people thought this might be valuable. By all means, let us know how else we can help you. Chemistry@vernier.com gets you straight to us three. Lane's not here tonight, but she's also in our group. Please let us know what we can do to help you. All right.
Thanks, everyone.
Thanks, folks.